In the fourth part of this video on the Java Collection Framework, we will discuss the stack class. We will examine two examples that make use of stacks. We begin with a discussion of the connection between the stack class and the vector class. Both classes predate the Java Collection Framework and have been in the language since the very first version. The vector class is like ArrayList, but all methods are synchronized. Synchronization is only needed with multi-threaded programs, a topic we have not yet discussed, which is why we have been using ArrayLists exclusively. Because no synchronization is involved, the methods in the ArrayList class are slightly faster. The stack class is a subclass of vector. What is unfortunate is that these two classes do not have the is-a relationship that we have explained is necessary when inheritance is used. It is not true that a stack is a vector. So making stack a subclass of vector is an incorrect use of inheritance. The real relationship is that a stack can be represented with a vector. Some languages, such as C++, provide a mechanism for using inheritance with such relationships, but Java does not. So the better design would have been to use composition instead. This program illustrates the problem that results from the fact that the Java stack class extends vector. It shows that it is possible to remove elements from the middle of the stack, which is contrary to what should be possible with a stack. Here is the stack of integers that will be used. In the first loop, we read in a collection of integers from a file and push them onto the stack. Scrolling down to the remainder of the code in the main method, this statement illustrates why making stack a subclass of vector was a poor design. Removing elements from the middle of a stack should not be permitted, only pushing or popping the top element. But being a subclass of vector, stack inherits all its methods, including the methods that allow elements to be added and removed anywhere. Finally, we pop off all the elements of the stack and output them to show that, in fact, an element has been removed from the middle. Next, let's run this program. Let's open the input file to compare what is in the input file with the output. Notice that the element at position 3 has been removed. Our last example in this part will illustrate using a stack to evaluate postfix expressions. Stacks are ideal for processing all nested structures, which include expressions. In particular, we will consider how to use a stack to evaluate postfix expressions, ones in which the operator is placed after the two operands. Postfix notation is also referred to as reverse Polish notation. One advantage to writing expressions in postfix notation is that no rules about precedence or associativity and no parentheses are needed. Let's consider the algorithm for evaluating postfix expressions. The expression is read in token by token. The action required depends upon whether the token is an operand or an operator. If it is an operand, which in our case will be an integer literal, the action required is to push that integer onto the stack. If it is an operator, which will be one of 5 arithmetic operators, we first pop 2 values from the stack, ensuring that we pop the right operand first and then the left. We perform the necessary operation and then push the result onto the stack. To help you better understand this algorithm, let's consider the postfix expression shown below and see how it would be evaluated using this algorithm. Shown below the expression is the arithmetic expression tree that corresponds to this expression. A postfix expression results by performing a post-order traversal of the arithmetic expression tree. Let's watch how this algorithm would execute on this test case. 8 is an operand, so it is pushed onto the stack. 4 is also an operand, so it is pushed onto the stack also. Plus is an operator, so an evaluation must be performed. The 4 is popped off the stack. Notice that the first value popped is the right operand. Then the 8 is popped off. The evaluation is performed, which evaluates to 12. So the result 12 is pushed onto the stack. 3 is an operand, so it is pushed onto the stack. Then the 2 is pushed on. Multiplication is an operator, so an evaluation is required. 2 is popped off. Then 3 is popped off. 3 times 2 evaluates to 6, so the 6 is pushed onto the stack. Subtraction is an operator, so an evaluation is needed. The 6 is popped off. Then the 12 is popped. The evaluation, 12 minus 6, is performed. Then the 6 is pushed onto the stack. We have reached the end of the expression, so the one value on the stack, 6, is the value of the whole expression. Now we are ready to examine the program that implements this algorithm. Here is the declaration of the stack of integers that is needed. The first step is to prompt the user to enter a postfix expression, and then we read it in. One important thing to note about this program is that it assumes that the postfix expression input is syntactically correct. We are using the string tokenizer class to tokenize this expression. The one benefit of this approach is that we can have the operators be delimiters and also returned as tokens. In this way, spaces are only required by adjacent operands. Let's scroll down to the main loop that processes the tokens. Each time through the loop, we get another token. If the first character is a digit, we assume that it is an operand. Notice that only unsigned integers are permitted as operands. If it is an operand, we convert the string to an int and push it onto the stack. One thing to notice here is that we are passing in an int, and the push method is expecting an integer. So auto boxing is automatically performed. Because both spaces and operators are delimiters, and both are returned as tokens, if the token is a space, we discard it. Otherwise, we assume it is an operator, and then call the method evaluate to perform the appropriate evaluation. Once the loop completes, the one value remaining on the stack is popped off and displayed. Next, we examine the evaluate method. Notice that both the stack and the token are passed as parameters. Two values are popped off the stack. It is important to pop the right operand first because not all operations are commutative, so the order matters. The switch statement handles each of the 5 cases. So for example, if the token is a plus, the 2 operands are added and stored in the local variable result. Scrolling down to the remaining cases, we see that after the switch statement, the value in the variable result is pushed onto the stack. Again, autoboxing implicitly occurs here. Next, let's run this program. Let's enter the same postfix expression that we used in the animation of this algorithm. 8, 4, plus 3, 2, times minus. Notice the output is 6 as we predicted.